Welcome everyone. In the last episode we looked at differentiating polynomial terms. You now know how to differentiate some of the functions you will encounter in the real world, whether it be plotting a car's movement down a highway or whether it be any other form of contextual example. But in this episode we're going to look at functions that are multiplied and divided. So let's get ready to add to our rule bank as we understand how to differentiate. So, product and quotient rule. Product, you've probably heard it before. You may even identify that it means multiplication. The product rule is what happens when we have two functions multiplied together, or should I say two algebraic terms multiplied together. So let's say that the h of x is the product of an algebraic term, the f of x, and another term, the g of x, multiplied. Well, what we can actually say about this is that the h prime of x equals the f prime of x, gx, plus the g prime of x, fx. You're probably sitting there thinking, what does that mean? But don't worry, because I'm here to help make everything understood. So, let me get out a blue whiteboard marker. And let's annotate this a little bit. So we have our function. An example of a h of x may be 3x squared times 2x. Nice and simple and straightforward. I may even make it 2x to the 4. What we're saying here is that in order to find the derivative of such a function, we need to take the derivative of this f of x term. So we take the derivative of that. We then multiply it by g of x. So we just let g of x remain 2x to the power of 4. But then we do the opposite. So both of these algebraic terms are differentiated on one side of the plus sign and also remain the same on one side of the plus sign. And hence, on the other side, we take the derivative of the term we didn't take the derivative of beforehand, and then we also just leave the first function as is. You're probably wondering, well, how did they come up with such a rule like this? Again, it's all linked back to first principles. That equation, that idea of taking those 2 points on the slope and getting them to come close to one another actually revealed this pattern known as the product rule. So let's have a go at actually using this, using the power rule example that we had in our last video. Let's find the h prime of x. So, just to recap, the h of x is 3x squared times 2x to the 4. They're multiplied together. Well, if we want to find the h prime of x, then we need to take the derivative of the first polynomial term. This one here. Remember the power rule? That very powerful rule that I taught you in the last video? Well, if we have a function, ax to the n, it's like what we've got here. We've got a coefficient a, x is our variable, and n as the exponent. Well, if we want to find the derivative of that, the slope that represents a function if we were to graph that, or should I say the function that represents the slope, then what we'd do is we'd get nax to the n minus 1. We bring the exponent down, multiply it by the coefficient, and subtract 1 from the exponent. Again, a pattern that we see from using that first principles equation. So let's differentiate 3x squared. We move 2 down, and we get 6, because 3 times 2 is 6. Then we have x as it is, and we subtract 1 from the exponent. And we've differentiated that term because it's 6x to the 1, and I don't necessarily have to write the 1. I'm going to put that in brackets just to make this equation look quite nice and simple to follow. What I then do is I look at my g of x, 2x to the 4, and I leave that as it is because I'm only allowed to give out one differentiation pass on either side of this plus sign in my general form. And this time I've differentiated the f prime of x first. So I have to make sure that my g of x remains the same because I can't give them the differentiation pass this time until after the plus sign. 2x to the 4 remains. But now there is the plus sign, and we do the opposite. So luckily, last time, the f of x, which is 3x squared, was able to get differentiated. So now it's the g of x's turn to have that kind of a privilege. So what we do is we differentiate the g of x. It's like finding the slope of this polynomial term, because we could graph 2x to the 4, and we could find the slope by taking the derivative. Again, that's what we're doing here. But with this function, it's really just two polynomial terms multiplied by each other. So it's a bit more complex than just a normal polynomial function. So what we do is we bring down the exponent and multiply it by the coefficient. 4 times 2 is 8. 8x to the 3 because we subtract 1 from the exponent. And now the f of x remains the same because it was able to be differentiated the first time round, at the very beginning of this function. So it remains 3x squared. And that's the product rule in a nutshell. If you have these two algebraic terms multiplied by each other, then you just follow this general form. The first term gets differentiated and then multiplied by the second term as it is. And then on the other side it swaps around, so the second term gets differentiated and the first term remains how it is. Again, remember that all the terms must be differentiated and they must appear once in their normal form. Also, the derivative should be longer than the original one because it has the parts of the original function in it. And then also the derivatives too. And that's a good way to check whether you've done it correctly. Because if it ends up getting a bit shorter, then chances are you've missed out one of the steps. But in general form, if we have h of x where they're multiplied together, that's how we differentiate when they're multiplied. Called the product rule. Okay, but now let's have a look at doing something a little bit more different, actually called the quotient rule. So I'm going to need just something to clean the board. There we go. Oops. And this is where we're actually looking at two algebraic terms which are multiplied by each other. Oh, sorry, divided by each other. Just did product rule. Okay, so we have the h of x, and it's equal to the f of x on gx. So again, those are just like algebraic terms. This function here is just two algebraic terms divided by each other. So let's say that the f of x is 2x to the 2, and the g of x is 3x to the 3. Let's find what the derivative of h of x is, the h prime of x. In order to do this, we need to follow a general form, just like in the product rule. And it's very similar to the product rule, but it has a little bit of a twist. The h prime of x is equal to the derivative of the numerator, the f prime of x, multiplied by the g of x, take, instead of plus, the g prime of x, f of x, so it's just like the product rule, but then it's all over the g of x squared. And this is where things start to get a little bit more complicated. So what we do is we take the derivative of the term in the numerator. We differentiate it. So we move move 2 down to the coefficient position. So we have 4x to the 1, so just 4x. And then we just write the bottom term as is, just like we did with product rule. And then, because the numerator has had its chance to be differentiated, on the take side, we've got to actually do the alpha one, the g of x. So we take the g prime of x and we differentiate it. So 3 times 3 is equal to 9. So we get 9x squared because we subtract 1 from the exponent. And then we multiply it by the numerator as it was. So as you see, we've got the original function parts in there, and then we've also got their derivatives as well. But here's a little twist with quotient rule. We need to divide it by the numerator squared. So it needs to be divided by 3x to the 3 squared. That's just the g of x as it was before. So key things to remember with this notation is that if we have a prime in there, it means take the derivative of that term. If it's just normal, like g of x there, then it means don't take the derivative, just rewrite that term. So you're either writing the normal term or you're differentiating the term and then putting the parts together into this general form that many mathematicians have actually proven through the process of differentiation using that first principles equation. So let's have one more quotient rule example, because quotient rule can be a little bit tricky sometimes. Most of the time, people forget to do the g of x squared on the bottom. It is quite important that you do this. Quotient rule does have a few little twists because of the fact that it is divide rather than multiply. So, let's go through one with fractions, because it's always interesting to try a more difficult problem. Okay. So I'll just clean off the board so I have a bit of space. And let's say that the h of x is equal to, and I'll go 8/5 of x to the power of 3 on 2 over, and I'll probably go 1.2 x to the 3/5. Now I'm not going to simplify in this video, but as you can see, it's a little bit of a tricky problem. The main thing I want you to get out of this is the fact that you actually need to know how to identify the components of quotient rule. So in product rule it's easy. We have a term and we have it multiplied by another term. So we know we have our little f of x term there, and we have another term that we generally label g of x within a bigger function, h of x. It's like having two functions multiplied together, two small functions, to make a bigger one. And then we differentiate that. But with this, with quotient rule, it's a little bit different. There is an easy way to determine it, and it's something that you need to become accustomed to. But it's something that's also very important. You can't get these mixed up. The f of x must always be the numerator. The reason being, the original equation, the h prime of x, says that we must take the derivative of the numerator first, because if we don't, we're going to end up with this on the wrong side of the take sign. And when we have plus for product rule before, it's not really a big issue, because you can have them on either side. But with take, it is a different issue. Because, let's think about it, 2 plus 3 equals 5. 3 plus 2 also equals 5. But if we have 2 take 3 equaling -1, that's not the same as 3 take 2, which equals +1. And that's why it's important to recognise which one's the f of x, which one's the g of x, within the bigger function, h of x. Again, these are like two mini functions in themselves, but they're all combined into one big function, the h of x. So now, we differentiate. We use this general form here to guide us. And I always recommend having these laws here written down somewhere in front of you. They're in the Formulae app too. But if you have them there in front of you, just while you're practicing, you'll eventually remember which component goes into which place. So, let us differentiate and find the h' of x. Because again, you'll probably see functions like this, especially if you go into higher level mathematics. You'll find ones that are complex like that. They're complex shapes. They're not necessarily parabolas or linear functions, but they are still functions, and we still need to know the slope of them. In fact, it's more likely that you get more complex functions than perfect functions like x squared, because the real world around us is chaotic more than ordered. Alrighty, so let's differentiate the first part. We bring the exponent down and we multiply it by the coefficient. Again, it's just that simple power rule that we learnt before. So we end up having the h' of x equals 3 over 2 times 8 over 5, x. And then, when we take 1 from 3 over 2, it's like having 1.5. So 1.5, take 1, it's going to be equal to a half. And that's the first term differentiated. We then multiply it by the second term, as it is, 1.2x to the 3 on 5, and then we take the derivative of the second term. And the derivative of the second term is simply 1.2 times by 3 on 5, and then it will be x to the 3 on 5 take 1. I won't simplify this as such today, but feel free to do so on your calculator or use decimal approximation. We'll actually do a little bit here though, just to make it simpler. And in order to do so, I'll probably actually just rub it out as I go along. But we have 8 times 3 making 24. And 5 times 2 making 10, so we get 24 on 2, square root of x. And once we got 24 on 10 square root of x, because again, x to the power of a half is square root x, you should know that from algebra, we're able to continue on. I just need a bit more space. So we get 1.2x to the 3 on 5, and then we simply take again, 3 on 5 multiplied by 1.2, x to the 3 on 5 take 1, and then we have the f of x as is, 8 on 5, x to the 3 on 2. Can't quite just fit it in, but hopefully you get the idea that that's all in the numerator. And now we have the denominator, which is simply that bottom term squared. And yes, while this is a more complex example, you will generally actually have these equations to differentiate. So hopefully you understand the process of just applying power rule within this general form. It does take practice, and you probably won't get it just by watching this video, because it's more of a complex rule of differentiation, especially for just a beginner. But if you practice, over time you'll understand it. You'll understand how all these components sit together, and how to actually get them. So thank you very much for watching. And in the next video, there's one last rule where we have brackets involved. It's called the chain rule, and it's where we have functions inside of functions. I'll see you then.